This is example 9-2, flow past a plug. So we have some kind of a pipe here, and that pipe has this plug inserted into it, and it's held by a couple pins. The distance between the pipe and the plug is given us at 0.2 millimeters, so it's not very big. And we're now asked how much flow is going past the plug. All right, so we'll have a little space there. So there's going to be some amount of, what do we have? Oil, I think, that's going to go past along here, right? Both sides, like all around. We're also told that we're supposed to think about this as two parallel plates, right? So if we kind of look from the top way down, then of course it would look something like this, right? Where the oil is going to be coming through this kind of a ring here, right? But we're told to take this and unravel it, make it two separate planes, right? So we can cut it somewhere like this, and we're going to say, well, we're going to have instead an opening that looks like this, which basically gives us two planes, right? Of course, they're not going to be closed on each end because they're touching each other there. But we're saying that the height is so small compared to everything else that it's going to feel like we have this this plane, these two parallel plates. So that means we know that this part, this separation, right, that is going to be the distance that we're given, 0.2 millimeters. And we know that this distance, right, that's just going once around. So we can say that's just going to be, we're given a diameter, right, so that just be pi times d. Right, it's going to be that distance there. So that's our, that's what our slot looks like, right? So now we can assume that this is laminar. So we can say we're going to have laminar, and let's put a little question mark behind it because we don't know it's laminar. We'll check that once we have the solution. Laminar flow between two parallel fixed plates. Fixed plates. What does that mean, right? That means we can go look at our solutions and pull up the one that we have for velocity, right? Because we'll need the velocity with which the oil is going past here. Once we have the velocity, we can multiply it by the area, and we can get the volumetric flow. So let's say we have u of y, right? Of course, it's going to change, right? Is going to be equal to 1 over 2 times mu times dx of P plus gamma times H, and all that times y squared minus AY. All right, so what can we say there? Well, we can simplify this term here because our pressure change is going to be linear. Same with our height difference is going to be, and we can express that directly. So we can say that would be equal to 1 over 2 mu times delta P over L plus gamma times, now what's the height change? Well, the height change is just the height of our little plug here, but the height of the plug is also the distance, the flow distance, so that's going to be L. So maybe we can just say, let's draw that in here maybe, say this is L, right? So that's just going to be L over L, which is nice because that will just 1. So that is y squared minus AY. So that means we can rewrite this, right? We could basically pull that out there. We can pull one of the L's down below. So we can say that would be equal to delta P gamma times L divided by 2 times mu times L, right? So I just find it easier to pull the L down here than to leave it up there. It doesn't matter, right? And the same, it will give us the same result. But this is now our value for our velocity. Now, if we want to get the flow, right, then we need to integrate that flow over the thickness, right? Remember that our velocity profile, right, is going to be changing, right? So we'll have one value up here, and then we have 0 at the bottom, right? That's where it connects to the plug. Oh, it's not going to be 0 at the top. It's not going to be maximum at the top. We're going to have our something like this, right? So now we need to integrate that to get to our flow. So let's say Q, right, is then just going to be integrating over our area of u of y, it's the one that we just defined, times dA. And if we refine that, we can say that's 0 to a, right, from the bottom to the top of u of y times, and the area is just going to be the width, pi times d times dy, right? If this is our y direction here, right, then that's how we'd integrate. All right, let's see what we can do there. We can plug in what uy is. We'd have that up there, right? So we can already pull out the pi d, because those are constants. Pi times d, integral from 0 to a. Now uy was delta p plus gamma L divided by 2 mu L. That's our uy. All of that times, we're missing our y terms up here. Oops. Otherwise that would be a very easy integration. So we have that times y squared minus ay dy. The front part is all constant, so we can pull that out. So we would have pi times d times delta p times gamma times L divided by 2 mu and L. And then we have integral from 0 to 2 over y squared minus ay dy. And of course that's a pretty simple one to do as well. So we can say equal to pi times d delta p plus gamma L over 2 mu L. And then what we get y to the third power divided by 3 minus a times y squared over 2, 0 to a. So that is pi times d delta p plus gamma L over 2 mu L. The zeros are 0, so we'd have a to the third divided by 3 minus a times a squared over 2, which of course just means we can simplify that there to minus 1/6. So we'd have pi times d times delta p plus gamma L divided by 2 mu L times minus a to the third divided by 6. All right, so that's our Q. And I think we can now just go ahead and plug all those values in to get to find what our flow rate is. So let's see, what do we have? We have pi. D is the diameter of the plug, which was 100 millimeters, so 0.1 meters. And then we have delta P, that's the change in pressure. Well, at the bottom of the plug it says it's 4 kilopascals, and of course on the top it's going to be at the atmosphere, so 0. So we go from 4 to 0, so that means we get negative 4 times 10 to the 3 Newton per meter squared. And then we have plus gamma L, so our rho is 880 kilograms per meter cubed times 9.81 meters per second squared. The L, we're saying was the height of the plug. What? That was 50 millimeters. So it'd be times 0.05 meters. And all that divided by 2 times 30.5 times 10 to the minus 3 Newton seconds per meter squared, right? That's our viscosity. And then we multiply by L again, which is 0.1. No, the L is going to be the 50 millimeters, right? So 0.05 meters. Let's not forget that we still have to multiply by our last term here. So we have to multiply that by minus A over 6. A is given to us as 0.2 millimeters. So that 0.2 millimeters would be 2 times 10 to the 4 meters. And that divided by, that part raised to the 3rd power there. And then divided by 6. All right, if we have all our numbers here, plug them in, I get 4.90069 times 10 to the minus 7 cubic meters per second. That's a pretty small number, I would say. Now, if we want to make this seem like something that we can grasp, right, then we can multiply that by 3,600 to get cubic meters per second, per hour. We can multiply that by 24 to get per day, and then times 7 per week. And if we do that, we get that this is 7.7997 times, that's the wrong number, slipped the line there. That gives us 0.29839 cubic meters per week. All right, so something that's 70 by 70 by 70, somewhere on that order, centimeters. So that's not a huge amount of liquid that's going past that plug. Right, so that would be our Q. And where do we have? Wrote it all the way top of the previous page. So Q is equal to, let's highlight this one, and then we can use the other one just to get ourselves an order of magnitude. Now, before we finish, we should check if the flow is actually laminar. Now that we have the velocity, or we have the flow rate, so we can get the velocity. So we can say check if flow is laminar. So we'll start by getting the velocity. Remember that for the Reynolds number, the velocity we want is the average velocity, so we can just say that's Q divided by A. In our case, that would be Q divided by pi times D times A, right? That's our that'd be this entire area right here. Right? That's kind of our slot, same as the area that would be kind of this ring. We can do that. If we plug that in, we get 4.90069 10 to the minus 7 cubic meters per second divided by pi times 0.1 meters times A, which was 2 times 10 to the minus 4 meters. And that gives me now the 7.7997 times 10 to the minus 3 meters per second, so a relatively small number, which makes sense. If my flow is very small, my velocity should be low. And then I can take that and stick that into our Reynolds equation, right? The Reynolds number equation, so we have RE is equal to V times rho times A, which in this case is our characteristic length. So that is then 7.7997 times 10 to the minus 3 meters per second times the density, 880 kilograms per cubic meters, and then that distance, 2 times 10 to the minus 4 meters. And we have to divide that by 30.5 times 10 to the minus 3 Newton seconds per meter squared. Plug in those numbers, we get 0.0450, which is of course less than 1,400, which means we had laminar flow. Which means that the approach that we took to find the flow rate was valid. Do a quick check here on your units, right? So we have a second there, so we have kilogram meter per second squared, that's a Newton, and then we're left with a square meter here and a square meter there. So we are dimensionless, so that's all works out. All right, so we have our flow rate past the plug, right, which was a third or something of a cubic meter per week, so there's not very much fluid coming past, but it makes sense, right? If it's only 0.4 millimeters wide, that's a pretty small gap.